Dear students, welcome back to the 4th class of Advanced Computer Organization and Architecture. Today we will discuss about pipeline architecture, and here we divide our total lecture into two parts. First one is basic of pipeline architecture, and the second one is the example of pipeline architecture. This slide is for the basic of pipeline architecture. At first, let's know about pipelining. So, pipelining is the process of accumulating instruction from the processor through a pipeline. It allows sorting and executing instructions in an orderly process. It is also known as pipeline processing. Pipelining is a technique where multiple instructions are overlapped during execution. Pipeline is divided into stages, and these stages are connected with one another to form a pipeline-like structure. Instructions enter from one end and exit from another end. The key idea of pipelining is a way of speeding up execution of instructions and overlap execution of multiple instructions. Pipeline is divided into two categories. First one is arithmetic pipeline, and the second one is instruction pipeline. In arithmetic pipelines are usually found in most of the computers. They are used for floating point operations, multiplications of fixed point numbers, etc. For example, the input of the floating point adder pipeline is x equal to 2 into 2 a into 2 exponential of a. Here a and b are mantissa. Mantissa means significant digit of floating point numbers, while a and b are exponents. The floating point additions and subtraction is done in 4 parts. One is compare the exponents, align the mantissa, add or subtract mantissa, and finally produce the result. Registers are used for storing the intermediate results between the above operations. And then instructions pipeline. In this, a stream of instructions can be executed by overlapping phase, decode and execute phase of an instruction cycle. This type of technique is used to increase the throughput of the computer system. An instructions pipeline reads instructions from the memory, while previous instructions are being executed in another segments of the pipeline. The pipeline will be more efficient if the instruction cycle is divided into segments of equal durations. Now let's know about pipeline conflicts. There are some factors that cause the pipeline to divide its thermal performance. Some of these factors are given below. First one is timing variation. All stages cannot take same amount of time. This problem generally occurs in instructions processing, where different instructions have different operand requirements and those different processing time. Then the data hazard. When several instructions are in parallel execution, and if they reference some data, then the problem arises. We must ensure that the next instruction does not attempt to access data before the current instructions, because this will lead to incorrect result. And then branching. In order to face and execute the next instruction, we must know that what that instruction is. If the present instruction is a conditional branch and its result will lead us to the next instruction, then the next instruction may not be known until the current one is processed. And then is interrupts. Interrupts set unwanted instruction into the instruction stream. Interrupts affect the execution of instruction. Data dependency. It arises when an instruction depends upon the result of the previous instructions, but this result is not yet available. Here is an analog example of pipeline architecture. Let's consider 4 users A, B, C, and D, and they do 3 works. The first one is cloth wash, then dry, and finally fold. So let's consider washer takes 30 minutes, dryer takes 30 minutes, folder takes 30 minutes, and stirrers takes 30 minutes to put cloth into dryers. Now if we do laundry sequentially, then what will happen? A take 30 and first 30 minutes for cloth wash, and second 30 minutes for dry, then third 30 minutes for folding, and fourth 30 minutes for put in dryer. At the same time, B is waiting for the work. Where A is completed the task, then B can start the works with the fifth with the same work, and it will complete it after 4 different 30 minutes. Then again C started this their work and complete it after 4 times 30 minutes. And then D will start and is complete their works in 4 times of 30 minutes. So the total time required here is 8 hours for 4 loads. But if we use pipeline architecture for the same work, then we overlap tasks. Here A can do their work with first 30 minutes by cloth washing, and then it go through the dry of cloth. At the same time, and the first position is empty, so we can start the cloth washing from the second 30 minutes, and at the same time the A go to the third for 30 minutes for folding the cloth, and the second position is empty, so B go to the second positions, that means third 30 minutes for his cloth dryer. At the same time, the first position is start, first position is empty, so in the third time 30 minutes time slot, C can start his work, and this is go on in similarly, and it works parallelly after when the position will be empty. So the total required time is 3.5 hours for 4 loads. So if we overlap tasks, then what will happen? Here have some instructions. First one is pipelining does not help latency of single task, it helps throughput of entire workload. Then pipeline rate limited by slowest pipeline stage. After that, multiple tasks operating simultaneously, and then potential speed up is equal to number of pipe stages. Then unbalanced length of pipe stage reduce speed up. Time to fill pipeline and time to drain its reduced speed up. Pipelining a digital system. The key idea is break big computation up into pieces and separate each piece with a pipeline register. So if you follow the figure, you can see in the first blue figure is mentioned the total time of works is 1 nanosecond, and the second figure mentioned that the we just separated each piece of work by using pipeline register, and here we just divided the whole throughput work into small pieces, and these are divided into 200 picoseconds. So the comment about pipelining is pipelining increases throughput but not latency. Answer available every 200 picosecond, but a single computation still takes 1 nanosecond. Limitations is that the computation must be divisible into stage size, pipeline registers at overhead. About pipeline have some good news and some bad news. The good news is multiple instructions are being processed at the same time, but that works because stages are isolated by register, best case of speed up of n. But the bad news is instructions interfere with each other. That's called hazard. For example, different instructions may need the same pieces of hardware in same clock cycle. Another example is instruction may require a result produced by an earlier instructions that is not yet completed. A pipelining processor has 5 stages in instructions execution. First was instruction phase, that is mentioned by IF. Second one is instruction decode and register read, that is mentioned by ID. The third one is execution operation or calculate address, that means EX. And the fourth one is memory access, that is mentioned by MEM. And the fifth one is write result into register, that is mentioned by WB, that means write back. A single cycle processor, all 5 steps done in a single cycle processor, dedicated hardware record for each step. Here is a demo structure of pipelining instructions. There is 3 instructions, instruction 1, 2 and 3, and if you follow the table, you can see in the right block is a clock cycle. Here is mentioned that every work is need for 1 unit time, that means 1, 2, 3, 4 and go on. So instruction first instruction is start working from the clock cycle 1 and then go to clock cycle 2 in instruction phase, then go to in clock cycle 2 where it work in instruction decode, and then go to the clock cycle 3 and perform with execution executive transition, and finally the memory, and then write back. But at the same time, the instruction 2 can start their work with the clock cycle 2, because when the clock start clock cycle 2, then first instruction go to for ID. That means the space for IF will be empty. So instruction 2 can start their work from the clock cycle 2 and then goes on. At the same time, the instruction 3 can start their work at the clock when the clock cycle is 3, because at the same times in instruction 1 go for the execute and then instruction 2 go for the ID. That means the IF place is empty, so in instruction 3 can start their work start its work from the clock cycle 3 and goes on. And the total instructions need 7 clock cycle. Here is an example of pipeline structure, and this example show the data dependency. If you follow, there is 3 instructions. First instruction is add register 1, register 2, register 3. That means register 2 and 3 will add, and it stores the result at register 1. And the second instruction is also calculating for add, and this will work with R2, R6 and store the result at R4. And the third instruction is that the R2 and R4 perform an addition operation and store at A4, but there is a dependency. The third instruction cannot use data at R4 until new value is updated. This is a pipeline hazard. Pipeline still is a delay in execution of instructions in an instructions pipeline in order to resolve a hazard. So in first instruction it can work sequentially, in second instruction it also can work sequentially, but in third instruction it cannot work sequentially, because it can throw ID in instruction phase and instruction decode, but it cannot do execute, because the updated value of R4 is not right yet. So it wait for the updated value, and this is called stall. So when the R4 is write back, then the third instruction can execute and finally go to the memory and then write back.